Hey everybody, welcome to our first 8.6 video. In 8.6, we're really going to be focusing on two things. We're going to be working on comparing linear, quadratic, and exponential functions and thinking about some of their properties, particularly in 8.6b. And we're also going to look at how you can create a quadratic equation from a table of values. So for today's video, you're going to need a note sheet, but you're also going to need to print out the handout that's on Google Classroom. So if you haven't done that already, please pause the video, set up your note sheet with the section, the date, and the I can statement, but also print out the handout for the second half of this video. And then resume the video as soon as you have both of those things ready. All right, so we're going to start by looking at some of the key characteristics of linear, exponential, and quadratic functions. And at this point, you know enough information to fill out this entire table except for the bottom right-hand corner because we haven't talked about, when we look at a table, what the common something is in that table. So I want you to take a moment, see if you can fill out as much of this table as you can on your own. This is really good review. And then resume the video as soon as you're ready. All right, so in terms of equations, we have obviously a number of equations for linear functions. So you might have written down y equals mx plus b. You might have written down ax plus by equals c, or if you remembered point slope form, you might have written down y minus y1 equals m times x minus x1. Any of those three would obviously be the equation of a linear function. Your sketch of a graph of a linear function could look something like that. And a linear function, in a table, we identify the common difference in the linear function. So an exponential function, we really only talked about one equation, y equals a times b to the x. And our exponential functions had an asymptote, and depending on the type of function, they curved something like that. And in an exponential function, when we looked at a table, those tables would have a common ratio. In other words, a common multiplier or divider to some extent, but we just called it a common ratio. So then for a quadratic function, again, we have three equations. Y equals ax squared plus bx plus c. We also learned y equals a times x minus h squared plus k, or y equals a times x minus p times x minus q. So our quadratic is going to form a parabola shape, something like that. And in the table, a quadratic function is going to have something called a common second difference. And we're going to talk about what that means today in our lesson, but it'll have a common second difference. So when we look at this, let's take a look at four different tables of values here and see if we can decide which are linear, exponential, or quadratic. And I want you to take a moment. You may not be able to identify which are quadratic yet, but they're the ones that aren't linear or exponential. So I want you right now to see if you can look at these four tables. I'd suggest writing them down in your notes. Identify which are linear, quadratic, or exponential. And then resume the video as soon as you're ready. All right, so our first table here in part A, we are subtracting 3 every time here. And so because we're subtracting 3 every time, that's a common difference of 3. So that tells us that we have a linear function. For part B, we are multiplying by 2 every time. And that tells us that we have a common ratio of 2, which means that this table represents an exponential function. And then for part C, if you look at this table, you're going to say to yourself, well, there's definitely not a common difference, and there's not a common multiplier. So I guess it must be quadratic, but I'm not really sure why yet. So let's see if we can figure that out. So if we look at our first differences, our common differences for each of these, we have -1, +1, +3, and then +5. Now, if you take this and do it again and find the differences of the differences, what you're going to find is that it's +2, +2, +2. This is what's called a common second difference. Our second difference is +2 every time, which tells us that this is a quadratic function. And that should sort of make sense to you, because if you think about it, a linear function, the x has an exponent of 1, which is why we have a common first difference. A quadratic function, the x has an exponent of 2, which is why we have a common second difference. And as you might expect, in Algebra 2, we'll look at cubic functions and quartic functions, and those would have common third or fourth differences. So we can look at D as well, similar situation. So if we identify first the first differences, we're subtracting 12, subtracting 4, adding 12. And then if we look at our second differences, we're adding 8, adding 8, adding 8. This function is quadratic. So this is everything that I wanted to put on our note sheet for today. I'd like you now to switch over to the handout that you printed out before you started this video on Google Classroom, because we're going to look at how we come up with the explicit formula, or in other words, the quadratic equation for a given table of values that are quadratic in nature. And so we need to fill out some information here. So imagine that you've got the function f of x equals ax squared plus bx plus c. That's what we're trying to come up with, right? Which means we need to find a, b, and c based on our table. And we can do that. We've got some information that's going to help us. And the first thing is that the a value, we can find that if we find the common second difference and then cut it in half, divide it by 2. In other words, twice the a value is the common second difference. Similarly, we looked earlier this chapter that we know what that c value tells us something too. And so we can find the c value pretty easily because the c value is the y-intercept, or in other words, it's the 0th term in our table when x equals 0. So it's pretty easy to find a and c. Now, to find b, it's a little more complicated. But it's not that hard because first we know a and c already. We're going to use a technique similar to what we used in 8.5 where we can now plug in a point and find b. So what you're going to do is you're going to take your ax squared plus bx plus c and you're going to replace the x and the y with any point on the table, any known x and y values that correspond with each other. We're going to put in a as the value we already found, we'll put in c as the value we already found, and then just solve for b. And once we've found a, b, and c, we'll be able to identify our quadratic equation. So let's go through an example together here. So imagine this is my table, and you can see this on your note sheet too. Our goal is to come up with our equation. So the first thing we're going to do is we're going to find our common second difference. And to do that, oops, let me rewrite this here. To do that, we need to find our common first difference first. So between each one, we'll find our common first differences. So we're adding 1, adding 3, adding 5, adding 7, adding 9, and adding 11. And then we will find our common second differences. And in this case, we're adding 2 each time. So that tells us that our common second difference is 2. And since a is our second difference over 2, in this case, a equals 2 over 2, or in other words, 1. So I've got my first of 3 coefficients that I need, a equals 1. Now, c comes from the y-intercept. So if we look right here, that's our y-intercept because x equals 0. So in this case, we just know right off the bat that c equals 1. Now, to find b, we're going to pick any other point other than the y-intercept. If you pick the y-intercept, it won't work because the x's will just wipe everything out because they'll be 0. So I'm just going to pick the second point instead. So I'm going to use 1, 2. So I'm going to plug this into the equation along with a and c. So we would say 2 equals a is 1, so 1x squared. But in this case, instead of x, I'm going to use the x value, which is 1, from that point 1, 2, plus b is our unknown, x is 1, and in this case c is also 1. So if we solve for b here, we have 2 equals, so 1 squared is 1 times 1 is 1. So 2 equals 1 plus 1b is the same thing as b plus 1. So 2 equals 2 plus b. If we subtract 2 from both sides, we find out that b equals 0 for this one. So if b is 0, then our final equation here would be f of x equals 1x squared plus 0x plus 1. So this quadratic would be f of x equals x squared plus 1. So there's 2 more examples on your handout. I would like you to pause the video and see if you can solve each example on your own. When you resume the video, I'll tell you the answers to both. If you get them both right, you can stop watching the video. If you get either one wrong, you'll want to see how I did them and see if you can come up with the correct equations. So take a moment, pause the video, try the next 2. All right, so the answer to the first example is negative 2x squared plus 3x minus 4. The answer to the second example is 2x squared plus 3x plus 2. If you got them both right, stop the video here. If you got either one wrong, I'd recommend you keep watching and see if you can figure out what your mistake was. So for this example, I would first find my second differences. So plus 1, plus 1, minus 3, minus 7, minus 11, minus 15, and minus 19. And if I go through here and find my second differences, I'm going to see that I'm subtracting 4 every time. So my a value is going to be negative 4 over 2, which equals negative 2. So that gives me the a value. The c value is right here. So c equals negative 4. So I'll put that in for c. And then to find b, I'm going to use a different point. And I always use the second one just because it's easiest. So in this case, I would have negative 3 equals, so a is negative 2 times 1 squared plus b times 1 minus 4. So we've got negative 3 equals negative 2 plus b minus 4. So negative 3 equals negative 6 plus b. And if I add 6 to both sides, b equals 3. And that's where we end up with our equation of negative 2x squared plus 3x minus 4. So let's look at the last example then. And this one's a little bit trickier. And it's trickier because I didn't give you the y-intercept, so we have to figure it out. So for this one, if we look at this, we're going to be adding 9, adding 13, adding 17, adding 21, and adding 25. So then each time we're going to be adding 4, which tells us that a equals 4 over 2, or in other words, 2. But we don't know c, so we have to think backwards here. Because if we think backwards, so each time we're adding 4, which means that this right here also has to be a plus 4, which tells us that this has to be plus 5. So that 5, to get from 5 to 9, we add 4. And that tells us in turn that right here we had to add 5, which tells us this prior value had to be 2. So that gives us our y-intercept, c equals 2. So then finally, we're going to find b, and again, I'm going to use that first spot to do that. So I've got 7 equals, a is 2, so 2 times 1 squared plus b times 1 plus 2. So 7 equals 2 plus b plus 2. 7 equals 4 plus b. Or in other words, if we subtract 4 from both sides, b equals 3, positive 3. So in this case, we got b equals 3, and our equation would be f of x equals 2x squared plus 3x plus 2. So that brings us to the end of our video for 8.6a. Give the homework a try and let me know if you have any questions.